Welcome back everybody to the sixth part of the Julia TicTacToe tutorial. In this part, we'll be writing code for Minimax, the algorithm that we explained in the last video. I'm gonna link this graphic again in the description, so you can kind of look at it while writing the code. We will be using this while writing the code. We'll be referring to this a little bit, and yeah. So one thing I forgot to tell you in the last video is that we're always assuming that X is going to make its best move, and even if X doesn't make its best move, right? If X makes a worse move, that's going to be better for us, right? Because if X because we are expecting a much harder case, and if X makes a mistake, we're obviously going to get an easier case, and it's going to be beneficial to us. So if X plays well, that's obviously going to be beneficial to us. So if X makes a mistake, obviously that's going to be beneficial to us, right? Because we are expecting a much harder case, but we got a much easier case. Okay, so let's actually start writing the code for Minimax, and make sure to name it Minimax, not Minmax, because Minmax is already a function in Julia. Look at that, Minmax. Okay, so Minimax. So our function Minimax is gonna take in uh, some parameters, right? So first of all, we need to know if we need to look at the board, right? While making choices, we want to look at the board. Okay. Now what else? We want to we'll be using depth to kind of differentiate between the levels. Like look at this, right? Here the depth will be 1 because we're probing one layer into the future. Here the depth will be 2 because we're probing two moves into the future, and this depth will be 3 because we're probing 3 moves into the future. So we need a depth to keep track of how you know where we're actually predicting what depth we're actually at, because that'll be helpful. If we don't have a depth, we won't be able to differentiate between this case and this case, right? Here the depth is 2, here the depth is 3. If we don't have a depth, we will not be able to differentiate, and it'll be a mess basically. So we'll take it in a depth. Another thing is you could change this code that we're going to write, the Minimax code, to actually use depth as a part of the score, as part of the decisions that the code makes. But that's going to be a bit that's going to take a lot of time. I'm not going to do that here. Uh, like basically, you can use a depth to kind of optimize and reach the fastest way to win or tie, right? Like instead of winning 4 moves into the future, if you could win 2 moves into the future, that would be better, right? So we want to make that choice instead of the 4 move one, but we're not gonna do that in this video. We're gonna just start writing our code. We're not gonna include that in our code here. Okay, so we want it no, so we want to know at which depth we are. We want to look at the board, and we want to see if the player is maximizing, right? Right. If the player is maximizing, then we pick the maximum. Otherwise, we pick the minimum, right? Okay. So since this is a recursive function, we'll have to write a base case for this, right? We'll have to write a case where we actually return something which will ripple back through our functions, so function calls. So so we want to write a base case. Let's write that base case real quick. So we want to see the result of the board. So we call check win on the board right now, right? If someone already won, if we're at a terminal case, right? If result is result is not nothing, right? Because we're returning nothing when it's not a terminal case. Uh, so it's asking me to use this for comparing with nothing. So I'm going to do that. So if result is not nothing, that means if result is something, right? It could be 1, -1, or 0, right? If we are at a terminal case, then what we do is we just return the result. right? We just want to return the result. That's what we did here. We returned the result up there, right? So this is gonna be our base case. Uh, Now, what if it's not that, right? What if what if the game is not over yet, but the player that we're playing for right now uh, is maximizing, right? If the player that we're playing for right now is maximizing, we want to maximize the score. How do we maximize the score? Well, now we need to make a random move, right? In Not a random move. We want to make a move in any of the available spaces, right? So for I in 1 is to 3, 1 to 3, j in 1 to 3, we want to loop through the entire board, right? We want to check if that space is empty. If space is empty, so board ij, if the space is empty, then we what we want to do is go and make a move, and we want to call minimax on that move, right? That's what we did here. We made a move, then we called minimax on that, and then yeah. So we want to make a move now. So let's make a move. Board ij equals ai, not ai. Over here it'll be player 2, because if we are playing maximizing, in this case it'll be player 2. That we're maximizing. Player 2 is basically ai or o, right? So you want to set it to player 2, and after we make our move, what we want to do is we want to call minimax on our board. We want to analyze all the sub cases here, and this time, if you notice, it's the red line, right? After if it's maximizing, the next turn will be minimizing, right? So we'll have to put in depth plus 1, because it's one move into the future after a current move. And if are we maximizing this time? We're not maximizing, right? So we're just gonna put down false for that, because the next player who is gonna play, that is X, is not maximizing, it's minimizing, right? So now look here. We actually changed the board, right? We actually made a move already. We don't want to do this. Let's quickly undo our move, right? After making our move, we just analyze all the sub cases, and then we undo our move. We're not really making a move here. We're not actually moving ahead in the game. We're just looking at the possibilities into the future, right? Now we want to see if uh, if whatever we have is the best move, right? Now we have to look at the score for each of these cases, right? We want to look at the score for each of these cases, and we want to get the maximum of these scores, right? So if you want the maximum of these scores, uh, so we want to write like a best score, and that will be what we want to actually do. So I'm going to call it minus infinity, because obviously anything will be greater than minus infinity. Uh, it doesn't really, I mean, anything if you compare it to, it'll just set it to that immediately, right? Because everything is greater than minus infinity. Okay, so we got our score. Now if, okay, so we want to check if our score is greater than, if score is, if score is greater than best score, then best score equals score. Now, there's a better way to write this, and okay, so there's a better way to write this. It's just basically best score equals max of score and best score, right? Really good opportunity here. It's the mini max algorithm, so why not use max, right? Okay, so after we're done checking every case, we got our best score, right? So we're gonna return our best score. There we go. So okay, so our maximizing one is done. Our maximizing code is done, and the minimizing code is almost the same, just couple changes. Uh, right? We want this to be plus infinity because we want the least score. Everything is lesser than negative infinity. Here, this time we're playing for player one because the minimizing player, and the next player will be the maximizing one. So we put it down true here. and this one will be minimum. All right. So I think that should do it. That's our minimax algorithm right there. Okay. So that does it for this part. We wrote our minimax algorithm. It's not going to do anything just yet. It's going to just return like a plus one, minus one, something like that. The code that we wrote so far is linked in the description. The final code that we'll have by the end of this series is also linked in the description. Thank you for watching. I'll see you in the next part.